Hi everyone. Today we'll be going over a A2 mechanics paper. Okay, so our first question, we have spent quite a bit of time just trying to decipher the scenario. But we have a cylinder like so. Oops, let me change that line width. New computer. Go down. There we go. So we have a cylinder like so. And we have a ball that's rolling around the sort of inner edge of the cylinder in contact with both the ground and the vertical edge of the cylinder. So it's moving around, and the first question is asking us to calculate the force that's being exerted by the vertical wall of the cylinder. So remember, it's all about balancing forces. So if it's moving around, it's got some centripetal force exerted on it by the wall of the cylinder, which is forcing it, to move around in the circle. Otherwise, it would pass straight through the wall of the cylinder. So this centripetal force, and that's given by mv squared over r. So this is just ma, because centripetal acceleration is v squared over r. And if we plug all of this in, we have the mass, we have the velocity, and we have the radius of the cylinder. Remember that the radius is half of this, so the radius is 0.3 meters. And if we plug this into our calculator, we'll get the answer of 3 newtons. So this was just considering the sort of vertical component of the force. And then the next one asks for the total force. So now we're going to have to consider firstly the force we've already found, and also the force from the bottom of the cylinder on the ball. Well, that's just going to be whatever is required to keep the ball from rising into the air or sinking into the ground. So it's going to be exactly equal to the weight. So the vertical force is equal to mg, which is whatever g f4. So that's going to be 4 newtons. So the total force is just finding, remember, it's like finding if we have one force this way, another force this way, and the resultant force is this one. It's like the hypotenuse of the triangle. So F total is the square root of Fc squared plus Fv squared, which is the square root of 9 plus 16, which is, of course, 5. And that's all there is to it. Okay, question 2. So here, this is about centers of mass. So they love these kind of questions where they have some relatively simple object, but not too simple, which is hanging from a point. So it's a uniform semicircular lamina. Uniform means that the mass is distributed uniformly, so you can use the equations that are given in the formula booklet, and you don't have to worry about any funky integration or anything. So here's our situation. We have some lamina, and it's hanging like so. And if you look up in the formula booklet, the distance of the center of mass of the lamina from the diameter AB, so this is A and B, I guess. So the distance here is given in the formula booklet for a semicircular lamina with an angle subtended of 2 alpha. So in our case, 2 alpha is equal to pi, because pi is the angle subtended. So alpha is not equal to pi, it's equal to pi over 2. So we plug in pi over 2 wherever we see alpha in the formula booklet, so it's going to be 2r sine of pi over 2 all over 3 pi over 2, which is 4r over 3 pi. And if you plug in r, which is a quarter, you get 1 over 3 pi. So the 4's cancel. And that is all that's needed for this part of the question, which is why it's only worth 1 mark. So I think the only possible subtlety here is recognizing that pi is 2 alpha, because if you read the formula booklet carefully, That much is clear. So now they want the angle the diameter AB makes with the vertical. Well, if we go back to the drawing, let's drop a vertical line down here. And you know that this line is a right angle. So we have a triangle. And we know that this distance, we just worked it out, it's 1 on 3 pi. And we know this distance, well, that's just the radius, because it's like that's obviously the center of mass is going to be sort of drawn down from the radius, the center of the thing, because it's uniform. So this is going to be r. And we notice we want the angle which the diameter AB makes the vertical is this one. So we know that the tan of this angle theta is opposite over adjacent. So that's 1 on 3 pi, 1 over r. And then if we take it to our calculators, we get that theta is 22.98 degrees. Now they change up the situation, and they're instead saying we're going to hold the lamina vertical. And the way we do this is we're going to apply a force that is acting at 45 degrees to the upward vertical. So it's like so. And so what forces are acting on this thing? Well, we have over here at the center of mass, we have mg acting downwards. And we have this new force of 6 newtons acting in this way. So now we're going to we notice the thing is in equilibrium. So you notice specifically that there's no moment about A. So we're going to take moments about A. And remember that the moment is given by magnitude of the force multiplied by the distance between the sort of axis point, the point you're taking moments around, and the line of action of the force. So the line of action of mg is like this. And we know already that this distance is 1 on 3 pi. And then we're going to resolve this guy, the 6 Newton force, into its 2 components. And you see that, oops, probably shouldn't do it there. It's sort of acting like this, so it's acting that way and also that way. And you notice that this component, this vertical component, it runs through A. So its distance from A to the line of action of that part of the force is 0. So that provides no moment. And that makes sense, right? If you're pushing through some pivot point, it's not going to make the thing swivel. So we really only care about this horizontal component. And you see that component is given by 6 sine of 45 degrees, which is the same thing as 6 times the cosine of 45 degrees. So the moments about A are going to be equal to mg times the distance, 1 on 3 pi, plus 6 sine of 45 degrees, times the distance between the line of action of this horizontal component of the force in A, which is just 2 times the radius. So we know m, we know g, we know 1 on 3 pi, we know 6, we know sine 45, and we know r. So you can get 20 newtons from this. So you just have to remember how to calculate the moment. And I guess recognize that that's what they're going to want. Okay, question 3. So we have a point up here on the ceiling, O, and a string down to some particle P, which is at rest at first on a maybe slightly more horizontal than that surface. And it's given a smack and sent off at some velocity v. And at some later stage, it's over here. And you see that the string has had to stretch. So we can use conservation of energy here. And so we know at this point, it's going, what energy is it going to have? Well, it has it has kinetic energy, 1/2 mv squared. And it has, the string has not been stretched. So the thing is, this is 1.6 meters. And the natural length of the string is also 1.6, so that's no problem. Now, at this later point, it's the length of the string is now 1.8 meters. So we're going to say this is equal to whatever kinetic energy V prime that the thing has at this point, plus the elastic energy stored in the string, which is given in the formula booklet as lambda x squared over 2L. And x here is going to be 0.2 because x is about the difference between the natural length and the length that it is, not the length that it is. So it's not 1.8, it's 0.2. So if we plug in the numbers on the left-hand side, you will get that this is equal to 9 over 40. And that's equal to, again, 1/2 mv prime squared. Plus, and if we plug in all of this, we get that this is equal to 9 over 40. So this means that the kinetic energy at the later stage is 0, which means that the velocity is 0. So we're showing that P was at instantaneous rest just at this point. So it started off with some velocity. It's being sort of, as it stretches the string, is having this restoring force exerted upon it until it's slowed down, and now it's probably going to start snap back. So we've proved that, and now we want to prove that P is on the point of losing contact with the surface. So what does that mean? Well, you remember that the reaction force is always going, if the thing is not moving vertically, then all the forces must be balanced. If it's just about to come up, that means that the tension in the string, or the vertical component of the tension in the string, must be just equal to the weight of the object. So mg must be equal to, which we know is equal to 2 newtons. And if we calculate 2 cosine of theta, which is, so if that's the tension there, and this is we want this component, well, we can notice that cosine of theta, where I'm gonna call this angle theta, you see that the cosine of theta is adjacent, this is t, times the adjacent component, which is 1.6 in position space. I mean, it's the same angle, right? So we can just use the position stuff. 1.6 over 1.8. And T is given in the formula booklet, lambda x over L times 8 over 9. And if you plug this into your calculator, you get this equals 2 newtons. So these two things are equal, and therefore the thing is about to lose contact with the surface. Okay, question 4. This is a kinematics question. So you're going to need to use, the equations of constant acceleration. So we know that acceleration is constant because the only acceleration it's feeling is the acceleration due to gravity, which is always constant, at least over a local area. So it's given this speed of projection, some v, and the angle is 40 degrees. And then it's going to go on this, like all objects, just under the influence of gravity and sent upwards, it's going to go on a parabolic arc. And at the end, its speed is going to be minus v. So you see that the horizontal component, the x component, vx, well, that hasn't changed. That never changes because there's no acceleration in the x direction. But the y component is exactly reversed. Actually, this isn't minus v. That was wrong. It has the same magnitude, but it's not actually minus v. But this is still, if this is vy at 0, then this is going to be minus vy at 0. So we can say that vy, the vertical component of the velocity, at 1.8 seconds is equal to minus the vertical velocity at 0. But you can also use the constant acceleration equations that tell you that this must be equal to the initial velocity minus g times t. So if we rearrange these two, we get that vy y at 0 is equal to 1/2 gt. And if we plug that in, we know that t is 1.8 seconds, so we get that this is equal to 9 meters per second. And we see that this must be equal to big V sine of 40 degrees. That's the y component. So therefore we can solve that V is equal to 9 over sine of 40, which is 14. Now they want the greatest height of B. So I'm going to call this SY. And with parabolic arcs, you can just use, the symmetry information, the symmetry of the system, to know that the greatest height is reached halfway through the arc. So it's going to be at 0.9 seconds. Well, that's going to be equal to initial velocity in the y direction, it's all vertical, at 0 times 0.9 minus 1/2 g 0.9 squared. This is the constant acceleration equation for distance traveled. And that's pretty easy to work out on your calculator. And remember that this is Vy at naught that I was using here. So it's 9, not the full V. It's 9 meters per second. Okay, so now we want the distance from O of the point at which B hits the ground. So this is going to be the x distance at the full time at 1.8 seconds. So that's going to be Vx at 0 times 1.8. And there's no acceleration in the x direction, so that's just it. There's no need to subtract a 1/2 AT squared. So this is going to be V cosine of 40 degrees times 1.8, which is 19.3. So there's really nothing to these ones. Just have to remember the constant acceleration equations. And if you've got a nice parabolic arc in your question, everything becomes really easy because the whole thing is symmetric. Okay, question 5. So we have the system set up, and then they release this particle, and the particle starts falling and starts pulling on B. So at some point, B is going to be in limiting equilibrium. So the natural length of this string is 1.4 meters, and what they're saying is that at some point, B will be just about to move, which is what the limiting equilibrium means. So it's at this point where the string has been stretched 0.9 meters this way and 0.8 meters this way. So it is where its natural, so it's 1.7 meters long, but its natural length is 1.4. So our extension x is 0.3 meters. So if we do conservation of energy, we get that from the beginning, so P starts here. So the energy in the system here, B had no energy, it wasn't moving, it wasn't doing anything. The string wasn't stretched, so it didn't have any elastic potential energy. So all of the energy in the system at the beginning was just mgh, where h is 0.8 meters. And this is now equal to 1/2 m at the later stage, mv of p squared, plus lambda x squared over 2L, again from the formula booklet, the elastic potential energy of the string. Well, we know M, so sorry, this is MP. And so we know M, we know G, we know H. This is MP again. We know V. Sorry, we don't know V, we're solving for V. We know lambda, we know X, we know L. And so we can solve this. For VP is 1 meter per second. Now they want us to find the coefficient of friction between B and the table. So when it's in limiting equilibrium, whatever force is acting on it, which is just the tension in the string, that makes it want to go to the right, well, that must be combated by the force of friction. Now the force of friction is equal to, so this is the weight, mvg, and this is the reaction force, which is equal to mvg as well, because the thing isn't moving vertically. So therefore, the force of friction, which is mu times r, which is mu mvg, and this is equal to the tension. And the tension given in the formula booklet is lambda x over L, which is 15 newtons. So then if you solve for mu, which is T over mBg, and this gives you mu is equal to 1/2. Okay, question 6. So this is a center of mass question. So I'm going to do this a bit rigorously. Usually with these questions, they only really require you to consider one dimension, but I'm going to show you that you can just use vector formalism and get it all in one. So the way that you calculate the center of mass is I'm going to use the vector x to represent a vector of coordinates, so x and y, and m total times x total is m1 x1 plus m2 x2 plus whatever amount of things you got in your system. So you can just add up all the bits as long as you have this sort of like weighted sum, a weighted average, where the mass makes a difference. Obviously, like something that's small and light is not going to have much of an effect on the center of mass. It's not going to move it very much. So everything must be weighted by its weight, by its mass. So the mass of the cone, the position of the cone, x cone, and I'm going to define my coordinates so that this here is 0, and then it goes up, y and x. So x of the cone, well, its x coordinate is just 0 because it's going to be directly above the center. Its y coordinate is given in the formula booklet for a cone. It's like 3/4 down from the vertex, so 1/4 up from the bottom. That's subtlety. Don't think it's 3/4 up from the bottom. And it makes sense intuitively, right? You think it would be close to the bottom because that's where most of the mass is. So it's given by 1/4 times the height. And so this is equal to 0 and 0.15. Okay, what about the particle? Well, x of p, and you can do this by trigonometry. And we're looking at this triangle here. So we see that this distance is going to be 0.4 sine of 60, and this one 0.4 cosine of 60. And that is what they are. So if we want the x coordinate is just 0.4 sine of 60. The y coordinate is 0.6 minus 0.4 cosine of 60 degrees, because you're going down from the top. And so this is equal to square root 3/5 and 2/5. Okay, so now we're going to do our sum that we had up here. So m total, well, that's the cone is 1/2 kilo and the p is 0.2 kilos. So we have 0.7 times x total is going to be 0.5 times 0.15 plus 0.2 square root 3/5, 2/5. And if you then you add these things up and you divide by 0.7, you get that x total is equal to 0.099 and 0.221. And so the question is asking you for the height above the horizontal surface. That's the y coordinate. So y is equal to 0.221 meters. Okay, so now they're sending p in motion around the cone with some angular speed, 4 radians per second. So let's think about this in a little more detail. It's the surface of the cone. Here's p. And it's being pulled by the tension of the string up like that. It's also got a reaction force coming out of the cone. That's R, that's T. And it's got mg acting vertically downwards as always. So this is our situation. So now I'm going to drop a coordinate system like so. And I'm going to start resolving along the coordinate system because they want us to find R. So that's our goal. Well, if we balance all the forces in the x direction, so fx, remember it's not moving in the x direction. So sorry, it is moving in the x direction. It's rotating. So this is going to be MA, and MA is mv squared over r. It's got this rotational motion. And therefore, we need to balance things in the x directions. This is why we're choosing to resolve along these coordinate systems. Your usual instinct might be to resolve along the sort of the plane of the cone, but that would be a mistake, because then your mv squared over r, which I think I should actually write better as mr omega squared. Those are the same because v is equal to r omega. That thing would be difficult to resolve. You would have to resolve that as well along that. So, whereas it is already resolved along the sort of flat x direction, is the omega. So this is our x direction, and the forces acting are, the mg doesn't have anything to say about this, but we've got t, and so if we remember that the apex of the cone had an angle of 60 degrees, so the horizontal component is t sine of 60 degrees, and there's also the vertical component of r, and then for that you need to know that if we carry in this would be 60, so this would be 30. So this is going to be minus r cosine of 60 degrees. So this is that component and that component, and together they give us a some movement. Now, what about the y direction? Well, the thing isn't moving in the y direction, so all of those must be balanced. And that's going to be t cosine of 60 degrees plus r sine of 60 degrees minus mg. So if we use this as a set of coupled differential equations, you can use a calculator to work out what the sine of 60 is, or you can use your similar triangles. And like any set of differential equations, you just solve them, and you get t is 1.96 newtons, and r is 1.18 newtons. Okay. Now they want us to find the speed of p. Well, this is kind of very, very easy for us, because we know that v is equal to r omega. That's why it's only worth 1 mark. So you just take r, you multiply it by omega, and you get 1.39 meters per second. Okay, last question, the differential equation question. So for this, you need to know that f equals ma, and a is just dv dt, and we're told that the force is equal to 1.16 e to the x. Now, you might immediately try and separate variables here, but the problem is that this thing is in terms of x, and this is not. This is v and t. So firstly, we need to use the chain rule and realize that this is equal to dv dx dx dt, just the chain rule. And then we recognize that this thing is equal to v. So this is equal to mv dv dx. So now we've got this in terms of x rather than t. So if we then separate variables, we get that mv dv is equal to 0.16 e to the x dx. And now I'm going to integrate both sides. And I'm going to use the limits that they give us. And I've talked about this before, but you can either do it by integrating indefinitely and finding a constant, or you can encode that information into the limit. So the velocity of p when it is at O, so when x is equal to 0, is 0.8. So I'm going to integrate from when x is equal to 0 to x is equal to some x later on. And at that point, v will be equal to v of x. So I'm finding a relationship between these top two limits. So if I integrate this, I get m over 2 v squared minus 0.8 squared is equal to 6 e to the x minus e to the 0, which is 1. And then if you solve this and take the square root, you get that sort of v is equal to square root of like 0.16 e to the x minus 0.16 all times 2 over m plus 0.8 squared. And that's all square rooted. And And then you see that this is equal to 0.8 e to the x over 2, remembering the rules about exponents. So you'll get, what you'll actually get is that the non-e to the x bits cancel out, and you're left purely with e to the x, which you square root, and then that square root becomes a half in the exponent, and you multiply those together. Now they want us to find the time taken during all of this. So we know what v is, and remember that v is just equal to dx dt. Well, we separate variables again. So we get that I'm going to take the e over here, which makes the exponent negative. E to the minus x over 2 dx is equal to 0.8 dt. And I'm going to integrate from when t is 0 and x is 0 to later on when t is some t that I'm looking for, and x is 1.4 meters. So this guy here, well, he's just minus 2 e to the minus x over 2. Convince yourself that's true. 1.4. And then if we just plug these in, you'll get that t is equal to 1.26 seconds. And there we have it. That's all done. I hope that's all clear. As usual, let me know if you have any questions on the forums, and I look forward to speaking to you soon. Bye.